just about the technicality of
Yes,
this.
go ahead.
Last one you like after you read the recursive function.
Yeah, the recursive function.
You said you have to prove it.
Yes.
So is there like a certain like
Structure? Yes. Yes.
question?
I said the structure. I said the structure.
Okay.
Okay, guys, there's actually kind of important, Thomas. In dynamic programming, you have to prove the recursive formula. As you did in the lectures, as we did in the recitations, you're gonna have to do in the homework too. Every single answer for dynamic programming question has a naive, and so you don't ask for it, and then recursive solution, which you have to prove. Okay, and then the dynamic programming solution, its correctness comes from the correctness of the recursive formula. And how do you usually prove that? Well, first you have to prove that it's a valid solution, that it holds by the constraints, right? Usually most questions you have constraints. You have to prove that it's valid, correct, and also that it's optimal. Now they're both very similar. You usually do induction on the thing that you're changing, on the thing that you're making smaller, because what is dynamic programming is basically taking our divide and conquer, where we make something smaller recursively, and then we're just saving computation, saving recursive calls that we call a bunch of times, and just saving that in the memory, and then we don't have to calculate it a bunch of times, therefore saving time. So you have to prove that it's optimal. So you do that with induction on what you're making smaller.
Like
the greedy. Yeah, there's and then that's also it's similar, but not the same. Thomas. Okay. All right. I am starting. If you guys want to talk, you're welcome to do so outside. All right. So last like 2 lectures ago, when we started dynamic programming and the last recitation, we did a couple of simpler cases, right? We did Fibonacci in the lecture. We did like we did the problem of the company that we had. Every boss can't come with his direct worker. So we had a bunch of different problems, and they were all pretty simple, right? We just did the divide and conquer solution, the recursive solution, and then it was very straightforward. It was just take the recursive solution and plug it in. But here in this recitation, we're going to learn a couple of, well, also first, for example, we did Fibonacci, which is a very simple recursive, right? It's just based off of the 2 previous ones, the dynamic programming. It's also pretty simple. We also have the maximum, the longest subsequence, the longest independent subsequence, the maximal independent subsequence, the MIS. You did this in the lecture, where you go backwards on all the elements, and each time you either add the element, and then you skip 2 elements because you can't add the element afterwards, or you don't add that element, and then you can just call it on the element beforehand, and so on you continue onwards recursively. But we're gonna talk about in this recitation 4 kind of techniques that we're gonna use that can be used to solve more advanced problems. The first one is a recursion with a number of recursive calls that we don't know. Like we saw in Fibonacci, there's only 2 recursive calls, right? We have here one recursive call and the other recursive call. But we're gonna see some that don't have a specific number of recursive calls. It's not just 2 recursive calls. It might be a different number of recursive calls. For example, what you guys learned the Monday, right? You learned yesterday the multiplication, chain multiplication, chain matrix.
Matrix chain multiplication. Yeah.
What you learned is like this was the recursive function. You then turn into dynamic programming. We take the minimum of k. So you have to try all the k's between this range, and this range changes depending on the function call. So what's the number of recursive calls here?
2 times k.
Well, 1, 2, yeah, 2 times k. But what's k? It changes per recursive call. So therefore, we don't know exactly, and that's why it's a changing number of recursive calls. A second technique we're going to learn is solving a different problem than the one that's defined to us. And then using that different problem that we defined that's easier to solve our original problem. Let's say, for example, we did that in the minimum independent set in a tree, right? When we said we don't know how to recursively solve this problem, we're going to divide it up into whether we take this node or we don't take this node, right? So we created two different problems that we knew we were easier to solve. And with both of those, we were able to solve our original problem of maximum independent set. Okay? The third technique is using more than one function for solving a problem, which is also maximum independent set. We use two different functions to solve one problem.
MAS was the one with the party and the box.
Exactly, the
Oh,
party,
okay,
exactly.
okay.
MIS is the one with the business that has a party and
Yeah.
to invite as many people as they can, but they can't invite a direct boss and worker, an employee. So we use two separate functions, whether we invite the node or we don't invite the node. Therefore, we're not solving the same exact problem. We're dividing it up into two smaller problems that are easier to solve. And then the fourth technique that we're going to see is doing
Computations.
three computations, exactly. Doing three computations to save us time in the future, whether it's calculating a sum or whatever it is. We'll see how to do those beforehand to save us time while doing the dynamic programming. All right, let's get right into it. We're going to solve three problems today, and then we also have one little presentation that I hope we'll get to. It's like a 15-minute thing, so let's try and get through this. Okay, so first, what is the problem? The problem that we're doing is the longest rising subsequence.
We can do this based on what we saw in the lecture, right? On the lecture we were talking about the longest is
Not exactly. It's that you're giving two different strings, right?
Yeah.
And then you have to do the longest common
Now,
substring.
right.
Subsequence.
Now instead of having two, can we just do like one string and the other is the string from 1 to infinity, and like we do that?
Well, you haven't seen the problem yet.
Yeah, I mean
That's the first one, but no, I don't think so. So our problem is as follows. We're given an input of a sequence of numbers from x1 until xn, like here. And the output we want to give is the length of, not the actual substring, a subsequence, but the length of the longest substring, xi1, xi2, length of xi, okay? That is a sequence that is monotonic rising, right? That for every element, the element afterwards is equal or greater, okay? Also, you can't change the order. It's another important thing to notice because it's a subsequence. Okay? All right, so let's see this example here. These are, we're just going to visualize it as buildings. The longest rising subsequence is this. Is if you look at the numbers here, basically you can't have 7, 1, right? Because 7 and 1, 7 is greater than 1, so you can't have that. But we can have 1 and then 4 because it's rising. And then 5 has already, it's the height of 7, and 6 is the height of 9. So we can really have this one, which is the longest one. Question is 2, 3, 4. Is this a subsequence that is rising? A valid subsequence?
Yeah.
Yeah, because it's going up, right? We have 1, then we have 5, then we have 6. Okay, so it's a valid one, but it's not the longest. We need to find the longest rising subsequence. Okay, is the problem understood?
But there is another, like, it doesn't matter, there could be a couple of the same
It can be a
thing,
couple.
it
We
doesn't
just
matter
need
what.
the length.
Just one.
Exactly.
Okay.
We need the length, and usually if they ask you to also give the actual subsequence,
Oh.
usually they ask you for just one. Okay, so we need to describe an algorithm that solves this in the most efficient way possible. So, because we're in dynamic programming, how do we solve these problems?
Make a table. Okay.
Now you're skipping ahead. What's the sequence of problems? How do we solve it first?
We make a recursion.
First, we do the naive. First, we do all the possible options, and that's the naive way. And then we do the recursive function, And then based off of the recursive function, we do the dynamic programming. Okay? So let's start with the naive. How are we going to do that?
We calculate all of the possible subsequence,
Exactly.
the ones that aren't rising, and then
Exactly.
and so on.
We check all the possible subsequences. And for each one, we check if it's valid, if it's rising. And if it's not rising, it's not even valid. And then if it's rising, we compare it to the maximum we have found until now. And then we just return the maximum. So how many of those subsequences do we have? 2 to the power of n. This usually repeats itself. Therefore, the runtime would be 2 to the power of n. It's actually like the length of this, like n times 2 to the power of n, because for each one, you have to check that it's rising, right? And you could have, at most, in worst case, it could be all of the elements that we need to check on all of them if they're rising. If also so with n.
Adriel,
Yeah.
you have the last time.
What?
You let the last time in the Zoom.
Not that like you have to.
Oh, they can't join? I sent the link.
Yeah, it's the song
You probably should let but
running.
Hannah joined. It's running. Tell them to try again. Or try and join from one of you join. It should be working.
Hey, carry on. Here's a mess.
All right.
Progress.
Yeah.
It works, right? Okay. All right. So can you leave though? All right. Now let's continue. So we said already the naive way. We just check all the possible options. We check on each option whether it's valid, and if it's valid, we compare it to the maximum that we have until now. Now, how are we going to solve it recursively?
This intuition to know this function.
The
Do you
function?
do something in your head when you do them, and how do you say? What do you say to yourself?
So
You feel
Well,
function.
why don't we, just because we're tight on time today,
Ah,
let's go through the questions, and then at the end, we'll go through the intuition behind them, okay?
So we
Let's
can
see a couple, and then that's,
We can-
it takes time also. It
Yeah.
takes time, but
it can start from the end. So we have a function that has only the index. It's f with the value of I. And we can do that. It's equal to like we take it or we don't take it. So
Okay. That's exactly what we're going to try and do, okay? So remember, recursive problem is just divide and conquer, right? So we need to make somehow our input size a smaller input for the same problem. That if I knew the smaller input, the answer to that, I could solve my bigger one, right? That's how we do it. So what are we going to make smaller? We're going to make I smaller the number of elements we can use in our longest subsequence. Very classic way of limiting the amount of elements we can use. So let's define f of I to be the longest rising subsequence for the sequence of 1 until I. So we bounded the amount of elements we can use. Let's try and calculate it recursively. There's 2 options, like you said, Thomas. Either xi isn't in the sequence, and therefore f of I equals f of I minus 1. We just do the one before. But here's where the issue comes along. If xi is in the sequence, then we have 1 element because it's in the sequence plus what?
fi minus 1, same thing.
Fi minus 1. But the problem with fi minus 1, you have to check that it's smaller than xi, right? Because it has to be rising. So you have to check that it's valid, right? In the recursive function, you're not checking afterwards if your solution is valid. If your recursive function has to check it. So if we're adding xi, you have to check that xi minus 1 is smaller than it. But here's the problem. When I call f of I minus 1, I don't know if xi is in the subsequence or not. Right? It could be that it's in and then I compare it and all is good. But if it's not in it, I really have a larger number over here that's actually in it. So you'd have to check for if you do it this way, you'd have to check for xi, like xi is in it. You'd have to check for f of I minus 1. You have to check the whole subsequence if it's greater than xi, if it's smaller than xi.
No, you have.
Or just the first one. But you have to go to the first one, and that could take a little bit.
Yeah.
Okay? So it's not a great solution. So we're going to use one of our techniques because the problem is a bit more advanced. So we're going to use one of our techniques, which is the second technique, is solving a different problem and then using that different problem to solve our original problem. Okay, so this is what we said verbally. That it's not what we said verbally is basically it's not the same recursive problem, right? Because each recursive call, if we add x of I, now we're bounding the longest subsequence beforehand. So every recursive call is a different x of I that we add, which is a completely different problem because we're bounding the elements we can use differently. So it's not the same, it's not a smaller input for the same problem. Okay? So like we said before, it wouldn't work. It's kind of complicated. You have to ship the whole subsequence before. Let's try, there's a couple of ways to fix this, and we're just going to see one of them. But let's define it a little bit differently. How are we going to define it differently? We're going to define f of I to be the longest subsequence, the longest rising subsequence of the elements, such that xi is in the subsequence. So before we try to take the longest subsequence, and then we divide it into two cases, if xi is in it or if xi isn't in it. Here we're defining it, it's only if xi is in it. So it's a completely different problem. It's very similar, but it's a different problem. And then we'll see at the end how we use this to solve our original problem. So first we need to ask two questions. First is, how do we actually calculate f of I for every I? Because remember before we got a little stuck, so let's see how we can actually do this. And then once we have that, how do we use that function to solve our original problem of finding the longest rising subsequence of all our elements? Okay, so our first question, how do we calculate it? Remember, it's the longest one such that x of I is in our subsequence. So now we don't have two options. It has to be in it, right? So now how are we going to define it? F of I equals 1, because we add it, plus, and now max of all the different f of j's, such that j is smaller than I, between 1 and I, such that x of j is smaller or equal to x of I. Why? Because I know that f of j represents the length of the longest common subsequence, the longest subsequence, such that x of j is the last element in it. So all I have to do is compare the last element, which I know is xj, to xi. And if this is valid, then the whole subsequence is valid. So therefore, by changing our problem and solving a little bit of a different problem, we can actually be able to check that no of 1 instead of having to compare it to check the whole sequence. Okay, so now we know how to solve it. Great. Also, we have to add 0 because we want max. If, let's say, I is 1, then you don't have any subsequence to check, so you just want the option of 0. Okay, so the proof of this is in the summary. There's a summary of this lecture in Hebrew. I didn't upload it yet. I will upload it after the lecture. But it's basically the same as usual. You have to check that it's valid. First, you have to prove that it's valid. And you have to prove that it's optimal. Okay? That our solution is optimal with induction on I. You use induction on I. The base case is f of 1. F of 1 is obviously just 1 because 0 is the only option. You don't have any option for this. F of 1 equals 1, which is in fact optimal. And then you do that with induction, full induction, up until I, and you've solved for I. And it appears it's the same thing as we did last time, so I'm not going to go over it. Okay, so now we're going to save how do we calculate f of I for every single one. We're going to keep all of f of I in an array the size of n. So the time to fill the ith cell is O of I. Why? Because the first cell we only have it's only based on one previous cell, right? The second one is based off of one previous cell, and the f of 2 is based off of f of 3 is based off of the 2 previous cells, and so on. Every cell is based off of the cell that we already calculated beforehand. So therefore, O of I, if you calculate it with a series, arithmetic series, then it'll take O of n squared time. Because 1 plus 2 plus 3 plus 4 up until n is O of n squared. Okay? The space is O of n. Now let's just see example of how we calculate this. So F is our dynamic programming solution. So for the first one, right, we have 1 plus the max of whatever, but we don't have any options, so it's 0, right? I mean, it's 0, so then it's 1 plus 0, 1. And now the next one, we need to check these ones, right, if they're valid. If xj smaller or equal than xi. So here, xj, which is 7, is not smaller or equal to xi. So this isn't a valid one to take, so therefore, I'm going to have 0 again. It's our only option. 0 is the max. So for it's also going to be 1. Now the next one, notice that 5, it's 5. So xj, this xj, x1 is not smaller or equal than 5, so it's not a valid option. But this one, 1 is smaller or equal to 5, so this is a valid option. So therefore, you'll see in the animation, they turn it green. And then we do the max between 0 and all the valid ones. F of j, in this case, f of 2 is valid. So what's the max between 0 and 1? 1. So we add 1 to that and we get 2. Okay? And then we continue on to this one, right? Now we have this one, which is the height of 6. So now these two are both valid, right? So we have f of this is f of 2, which equals 1, and f of 3, which equals 2. So the max between those and 0 is 2. So we'll take 2 and add it to 1. And we get 3. And so on and so forth. Now for this one, the only valid subsequence before it is this one. So therefore it'll be 2. Same thing for this one. And then for 7, for index 7, it's 5. So it has all of these to choose from. But which one is the largest? One of these 2's. Doesn't matter which one we take, 2. So then we add 1 to it and we get 3. So on and so forth. Now we only have that one to choose from because 8 is a little bit low. And then 9 is a bit higher. And notice that for 9, we can also take 4, which is the same height. They're both the same height because it has to be greater or equals. So on and so forth. And we finish. Is this understood? Of how we calculate the dynamic programming for our f of I function.
Doesn't it have to check like everything cursively? So it like you're in the ninth one, okay? So
Yeah.
you check all of the ones that are smaller than 6, and then you select the highest one. You have
Exactly. So you check all of these recursively. You compare these. Two. So this one's valid. So this one's valid. All of these are valid.
grab the highest one,
And you grab the highest one. Exactly. You grab the highest one and add 1 to it.
and you don't care which one you grab.
No, doesn't matter.
Okay.
Exactly. And you also didn't need. We didn't go into how you can output the actual subsequence. We're just outputting the length right now.
Yeah.
Okay. All right. So now that we have that function, we know how to calculate this. And how long does this take? What's the time of calculating this whole? All right.
And square.
And square. So we know the time, but now we need to solve our original problem. Our original problem wasn't only the longest subsequence up until I that has to include I. It could be anywhere here, right? The subsequence can be anywhere. So all we're gonna do, where's the answer gonna be? A lot of times this is in one specific cell, but in this case, because we're solving a problem a little bit different of a problem, here it's in some sort of cell. So we're gonna go through all of them and take the maximum. Right? In our previous example, you see the largest one is actually in the second to last. It's not in the last one. Because the last one has to include this element, which might not be optimal. So we have to check through our whole array and return the maximum one. Okay, to sum up, we used in this question the technique of solving a problem that is similar to the problem that's defined to us in order to solve the original problem. Also note that we don't have a specific number of recursive calls, right? It depends on where we are, because it depends on all the recursive calls beforehand. I'll go back to our formula. This is our formula, right? It's max of all the j's. Of all the j's that are between 1 and I. So the number of recursive calls is actually bound, it's I is the number of recursive calls, and I changes per depends what we put in to the recursive function. So there's actually two techniques here. It's
bound by n factorial or
n factorial.
like the bound of the recursive calls. No,
Like if we had just solved it recursively, it's bound by 2 to the power of n.
okay.
Usually the recursive function does the same thing as the naive solution, right? Like a lot of times you just
Exactly.
also compute all of these, and the only benefit is that when we go to the dynamic part, we can use them differently.
Exactly. So also maybe this will help with your intuition of how to come up with the recursive formula. Is remember that the naive is just checking all the options. The recursive formula is divide and conquer. You can't just check all the options. What you have to do is you have to define some sort of parameters. They're going to get smaller every recursive call. And if you know the smaller answer, you can solve the bigger answer. Okay?
Yeah.
All right. This is actually a really fun question. It's called the game. It's literally just called the game. If you ask anyone who's learned this course, tell them the game and they'll know the game. Okay. So what is the game? On a table, we have n different cards in a line. And on every card is written its worth. And we can see all of the different cards. 2 different players are going to play this game in turns. Every player on his turn can take a card from either end. So I can either take from the end or from the beginning. Those are my only 2 options. I have to take a card. It has to be from the end or the beginning. The goal of each player is to get the most amount of money. Okay? So we need to define an algorithm that tells the player every turn what's the card that he can take that will provide him the most amount of money at the end, right? Because it could be you're taking a very valuable card now, but in the end it doesn't pay off because the other player gets a lot of other valuable cards.
You assume that the other player plays perfectly.
Exactly. So first let's see an example, but we assume that the other player also plays perfectly. It's already like game theory, but we can assume that it'll do the smartest play also. So let's say the first player takes the 20 card, which wasn't that smart of a move, because then player B can take the 100, and player A takes the 50, player B will take a 30, player A will take a 30, and 20, and 10. At the end of the game, you can see that player B actually won because he has 150, which is more than the other side, which is 110. All right, so now let's define the input output. Input are the numbers, V1 until Vn are the numbers, which indicate the values. And then the output is how much money the first player can win by the optimal moves that he can make, with the assumption that the second player also makes the most optimal moves. Okay, so naive solution. First off is the question defines. Everyone understood it? Okay, it's the game. Now you guys know. All right, so naive solution. Naive is they compute all the options, right?
Yeah.
Compute all the options and then take only the valid ones and the maximum one.
How we compute all the options given the other player, right?
Exactly. So you can compute all of the options. First, you have to compute all the options for every turn. We can either take the end or the beginning. So we just check both options and check which one's more. And therefore, we have at most 2 to the power of n different games. But we have to also define a certain algorithm or a certain I just think I'm gonna.
I know that.
A certain algorithm or a certain sequence that'll not sequence, a certain whatever algorithm that'll check the
Strategy.
what strategy. It's not exactly, but it could be. strategy or algorithm that'll check if the solution of the other player is optimal for the other one. Right? 'Cause if you don't know that, what? Mechanism, there it is. It's
Okay.
you have to create a mechanism that'll allow you to check whether or not the given a certain game sequence, if that was really optimal for the other player. It's a little bit difficult because that's why it's also left for food of thought. Because basically what we're trying to calculate. So
Is it required a lot of the time to take first the naive solution, or can we stick to the recursive formula?
usually it's required. If it's not stated, probably it won't take off points, but really you can just the nice solution is always compute all the options, check if it's valid, and then check, and out of all the valid ones, choose the most optimal. You just write that in words.
Like sometimes they write solve with dynamic algorithm. This is when you have to like do it properly, and sometimes
Yeah.
they specifically ask write the recursive, prove it, and now do
Dynamic program.
dynamic. And this is when you learn to
Yeah, if they're right, just do the recursive one.
Yeah.
If they're right, do the recursive solution and then the dynamic programming solution. You don't have to do the naive. But if they're right, give me a dynamic programming algorithm, you have to do the whole thing. Okay? And the runtime of this is to the power of n. Okay. Now the recursive solution. So remember in recursive solution, we have to make the input smaller, right?
Can we can try? Wait,
Yeah, go ahead.
So you have like I and J, which are like the right and left cards, and you go, okay, we have to take the max of taking the right card and taking the left card.
Exactly. Okay.
And the problem now is again, what do we give to the other player?
Exactly. What does the other player choose?
I mean, it's always the best one, right? So
Exactly.
the maximum.
So I think you have the right thing. I'm just gonna show the actual formula because I'm sure that you're gonna be like, that's what I meant. So I'm just gonna jump to it, but first, two players together, they're both gonna earn together the total sum of from I to J. Like you said, we're gonna solve it from VI to VJ. Our function is gonna get I and a J, and it's gonna solve for that from that situation. So together they'll earn the sum, right? So therefore, what the second player earns is what the first player is gonna lose from the sum. Okay? So we use that, and these are our two. This is for player one, this is for player two. You can see also that they're the same. So given an I and a J, if I equals J, it's our base case, you only have one card to take, right? Our base case, if I is smaller than J, so we can take from either end. So we want to calculate the sum of all the cards that are left, minus, we want to minimize what the other player is getting. Because what the other player gets is taken away from my sum. So I want to minimize that. So it's the minimum of taking, if I took the first card, if I took the ith card, or if I took the jth card. Okay? So I calculate the minimum between the second player's function of both of them. And I subtract that from the total sum. Okay, does the recursive function make sense?
yeah, the computation looks awful, but yeah.
Computation looks awful. Okay.
We use the sigma here. So
Well, what?
like when I tried to solve it, I just did the minimum, like without the sigma. I just did when I use this the J minimum for both of them. Why
You
do I
just did
need the
minimum
sigma?
here
Yeah.
because
Why
you
do I
want
need
the
sigma?
function to output the value that the first player is going to get, right? At the end of the game.
Oh, how much? Okay.
How much he's gonna
for
earn.
the sum.
Exactly. That's why I need the sum minus with other players. Because if I just took the minimum, it would be, yeah. If I just took the minimum, it would be how much the other player can earn minimally.
What's the order of computation item? Like we should have computed this charges segments first, then the long ones.
So we'll get there eventually. You're talking about already in the dynamic programming solution, or just even in the recursive?
For this formula, right? Because we need to know. I mean, yeah.
For this one, if you're doing it recursively, you just give it 0 and n. And it will compute that.
Because okay, yeah, I guess I know what dynamic programming, but like if we use P2, we have to already know it, right? So
Exactly. Exactly. So let me just, maybe this will help a little bit. If we look at those two functions, we can see that they're equivalent. They're the same exact function. Therefore, we can just write this as our function. Right? Because it doesn't matter if P1 or P2 is playing, we're assuming they're both playing optimally. Therefore, the function is really the same for both of them. Okay, is that understood, that step? Okay. So now we have this. It might answer your question, but it's a bit easier to solve because now we don't have to jump back and forth between P1 and P2. We only have one function to solve. So now I might draw this because it's just easier to understand when you see the drawing. Okay, so we're going to keep a table size of O of n squared. And every cell is going to take two recursive calls, right? This recursive call and this recursive call. Plus, also, we need to calculate the sum, right? And the sum changes. So it'll take us at most O of n, right? The sum takes the most O of n. Therefore, the subtotal, because each recursive call will be stated previously, and the subtotal will be O of n per cell, which O of n squared cells would be O of n to the third power. Now, just because I get upset when people just like wave their hands in the air, so let's just do this really quickly. How are we going to fill up this table? First off, what's the size of our table? Yep. N by n, right? And let's say this side is I and this side is j. That's usually how it's done. You can switch them. It's just confusing for you. Okay, so now what's our base case? What can we fill up? Which cells can we fill up first?
Diagonal.
Exactly, the diagonal. When I equals j, that's our base case. When I equals j, this is just our diagonal, right? So this is our beautiful R right here. So this would be which V?
VI.
Which VI? Which number?
1, 2, 3, 4. VI.
0.
Yeah.
This is V0. This is V1, V2, so on to Vn. Correct? And now how do we compute each cell? Remember, when you also solve these problems that I'm programming in your solution, you have to also explain the base case and how you fill it up. What were you gonna ask?
Yeah, if you have n-1 in the corner.
Well, technically, yeah, you're right. Wait, it just depends on the problem. Let's go back to the problem.
It says that it is V0 in the upper left corner.
1 second. It's until Vn, so it's V1 until Vn. Sorry, my bad. It's V1 until Vn. Are you right, Artem? Okay, so now how do we fill up each cell? Exactly. You know so well. By the recursive function, right? So for each cell, we have to calculate the sum, which takes O of n. So we compute the sum, and then we subtract the minimum between P of I plus 1. So let's say we're calculating this cell first. Pi plus 1 would be this cell, right? Because we're just going to, would be, it's the other way around. We're supposed to do it. This is why I like when people actually solve it, because then you get to see them confused instead of you being confused. But it's supposed to be the other way around, right? Because Pi plus 1, it's supposed to be from 0 to n for j. And for I, it should be the other way around. So, because j minus 1. Oh, wait a minute. Actually, this is okay. We're just going to solve it. Because I has to be smaller than j, right? So if I is smaller than j, we only need half of it, right? We need 1/2 or the other half. So if I is smaller than j, that's this one, right? That's this half. So this whole half we can ignore. Okay. Now, the minimum of Pi plus 1 and j. So Pi plus 1 would be the one above it. Pi j minus 1. So when I did this earlier, I might have gotten confused that I just did, it's the minimum between these two.
Oh, but here the first column is also I. Ah, no, it's not I equal J, but like is I. Because J is 0 in that column, and I is like
Wait a minute.
not greatly smaller than this one.
Hmm?
It's not I is not greatly
Yeah.
smaller than J in this column.
In this column?
In this column, yeah, because J.
Oh yeah, you're right. You're right. We
is
need
0
the
and I
upper
is
one.
1, so
Yeah,
it's
you're
not-
right.
Okay,
Okay. So this one is
it's really important.
it's very important. Okay, from the top. This one V1 until V2, V3, and now we're
Yeah.
calculating the upper half, not the bottom half. My bad. So for this cell, what is it based off of?
Oh, now we have it.
Now we have them.
Now I have
miracle.
J minus 1.
Now we have
yeah.
I plus 1, which is V2,
V2 and
and V1. So we take the
Okay.
minimum of them and subtract the sum of
VK.
the first two, V1 and V2. So if let's say the first card, V1 is 4 and V2 is 8. So V1 would be 4 and V2 would be equal to 8. And then we take the sum, 12, minus the minimum between those two, which would be minus 4. So we take 8. And so on and so forth, we fill up. And now we understood what a cell represents and how do we fill it up? You also have to explain how you fill the thing up. So how you fill the table up is just by going by the diagonals. As such, sometimes we do it by rows, sometimes we do it by columns, sometimes by diagonals. Okay? Because each cell is based off of the one right to it and the one below it. Okay? So you have to do it by diagonals. Because if I would just do it by row, I'm missing the one below it. All right. Okay. Now, how can we make that a little bit better? Doing pre-computations, because we have to, the heavy computation was doing the sum, right? The sum took us O of n. So we want to be able to access the sum from sum k equals I until j in time of O of 1 for every single I and j. So how are we going to do that? We're going to do, this also comes up a lot, and we code it prefix tables. So we're going to calculate the sum of the prefix. So for every I, we're going to sum up from k was 1 until I of all of the k's. So for our first element, it'll be just the first element. For the second one, it'll be sum of the first two. Third element, sum of all of them, so on and so forth. Right? So if I equals 0, then 0 goes from 1 to 0 is just nothing. And then this is basically our recursive function that we're going to call it S on the previous one plus the sum of the current one. And this is going to help us to eventually do it in a smart way. So the time and the space for computing all the prefix sums is O of n. So we just go through the all the elements. And then in order to calculate the sum between an I and a j, because right now we only have the prefix. So how are we going to calculate it? The sum of from I until j equals the prefix of j minus the prefix of I. How does that look like? If let's say we have prefixes here. Oh, actually, there's actually an example. Instead of drawing it, I'm going to do this a little bit. These are our cards. How is the prefix? The prefix table is going to look like this. Each time we just compute it based on the previous ones. So this is our prefix array. And then let's say you want to calculate between I and j, between those I and j's. So what are we going to do? We're going to do 140, which is this element, minus 60, which will give us not 60, wait, minus 50. Minus I minus 1. You guys are correct. 140 minus 50 will just give us the sum. And the intuition behind that is that this gives us the whole sum for this one. And then this one gives us this one. So everything minus just the beginning will give us the actual sum we need. And that is we're able to do that in O of 1 for every cell. For every single sum, we can now compute it in O of 1 by using our prefix sum.
So instead of doing n times n squared.
Exactly. Now it's O of 1 for
n?
every cell.
Yeah.
N squared cell, so it would be O of n squared.
In my brain fog, I didn't hear why you crossed out the bottom.
The bottom one, because in our recursive function, I is smaller than j. right? Our recursive function I has to be smaller than j. So when j is greater than I, we don't need to compute that because it's not part of our recursive function. Also, it's part of the definition of the thing. If j was bigger than I, then the game would have gone like past, it doesn't really make sense. So our I and j like get closer and closer and closer. When they're together, that's our base case. So it can be that it'll continue onwards because then what cards do you have left to take?
Sure.
Okay. Questions on this one? We're doing good time. 45 minutes. We got this.
Do you have a way to return the path, or like which cards you have to choose?
Ooh, return the path of the cards.
Where's the answer?
It's a good question. First off,
Forget about this.
great question. Great questions. This is what you're gonna have to be able to explain your solution, where the answer is gonna be, how you compute the answer. Right? So let's go back to our recursive function. This is our recursive function. And we want p of 0 in n, right? So when I equals 0, this one's I. So when I equals 0 and n. So right here will be where the answer will be for your question. For your question, you asked what about the path. So a lot of times in the path, you can either keep, there's two main ways to do it. You either keep another array, another 2D array, where you keep each cell, which cell did you chose from before. And then it's very easy to retract the path. Because in each cell, it tells you which cell it took it from.
My question was if you can do it dynamically, but that's not.
What do you mean dynamically? Like
what we saw in the lecture is that you can just see from where the increment is.
Exactly. So that's the other way. There's one way where you just do a copy of the table and save each choice. And the other one is being able to really look at, it's based off of this one and this one, right?
Sometimes.
Here, no, in this case, it's only based off of those.
Okay.
And sometimes in other questions, it could be the diagonal. But in this one, it's only the min between these two, right? So it's a little bit more complicated here than in some other problems because you have to go back to the sum and get the sum. And you have to calculate, is the sum minus this one equal to this? And is the sum minus this one equal to this? And then you know which one to go to. Okay? And you can do that going backwards. That's usually, those are the two main ways of we can retract the path. And if you're unsure, like if there's no demand of the question, if you can't figure out exactly how to go backwards and you're not sure, just keep another table. Why not?
Sure.
And as they say, only use n squared space and that's it. Okay. Last question for today, and then we have that final little slides. Okay.
Worst question.
That's why I saved it for last.
Yeah.
Okay, little story. For the first years of computer science, there are n students that signed up.
330.
But what?
300.
300. Okay, let's say, and we don't know exactly. We're given a list of them sorted by their names alphabetically. In addition, we know who's a friend of who from the students. And it's given us by pairs of students. That's how we know who's friend of who's. And the secretaries want to have to divide up the n students into k different classes. Let's say, for example, here's our list of people. There's n people. These are our friends. They're given us as pairs. So Avram is a friend of Dymanic. And the secretary has to divide up all the people into k different classes, and you can only divide them up by inserting a line. You can't choose. Dani, Chaya, and Tova are all going to go to one class.
You can move them.
You can't move them. You have to you have to basically divide them up. We'll see obviously how that ties into the whole solution. So we have k minus 1 division lines, right? And here, like we said, the only way that we can divide them into groups is by sliding in divisors into the list of names. And the goal of the secretary is to divide all the students up into K groups such that the most amount of friendships are retained within a class.
So the friendships and the order is independent.
Exactly, they're independent. Exactly, you're given a list of friendships, and you're also given a. Okay, and in every class, we need to have at least one student. Why is this super important? If we didn't have this, we just put everyone into one group, right? So therefore, we need to have at least one in every single class. Okay, so now defining it already. Like computer scientists like it. Input output, already not just story time. So the input is a list of n students and also a binary matrix size of n on n that describes the friendships between them, and also a k whole number, a natural number, which is smaller than n. And then the output is the number of friendships that are kept with division of all the names into k different groups, such that every group has at least one student that keeps the maximal amount of friendships.
So both the groups and the maximum amount of friendship inside each group, both of them,
Both the what?
the groups,
Yeah.
and the amount of friendship in each group.
So really, we just need to output the number of friendships.
Just a number.
Just the number of friendships. We don't have to give the actual where to divide them up. Okay, just the maximum amount. All right, is the question understood? Problem understood?
Yeah, we just have to divide the groups that have at least one student, such that
Exactly.
we have the highest number of friends in the.
Is the final runtime underscore K?
Yes. Leave.
I got it.
Get out of here. Don't listen to him.
I'll get back. So okay, we have
Okay.
the naive solution first.
The naive solution, yes.
So-
What's the naive solution?
The Stirling numbers of the second kind. I don't know. Partitions of sets.
Complete all the solution. It's always
Compute
the
all
same.
the solution.
It's always the same.
Yeah, but you can't complete all the solutions. That's the point. Because you have empty groups, right? Or,
Okay, and you check if they're valid.
Okay.
Exactly.
Sure.
You and then
I thought you have this.
see, got me the code. This is the most fun part. I put
Exactly.
everything. What is correct? Amazing. I take the best of them. That's it.
Exactly. She said it better than I could have. So exactly like she said, you just check all the different options. How many options do we have?
This is where I start.
K,
Oh my god.
K minus 1, choose n plus K minus 1.
Yeah,
Why?
that's the other way around. Okay.
Sorry, my bad. Whatever, that choose n. Why? It's exactly like the number of options to divide up n different balls, n different identical balls into k different baskets, right? Because we don't care. We can only divide, like the balls are all identical because we can only choose where to put the divisor. We can't. The students are not different, right? We just can choose where to put the divisors.
Thinking like that skill.
Exactly.
It's K.
It's not n choose k.
It's something. It's a problem called
N choose k would be choosing k items from n, and we're not choosing.
Okay, choose N. Like
No,
I
exactly. I understand where you're going with this. You want to basically say we have n different divisors,
okay.
right? And we have n minus 1 different places to put them, right?
I'd explain like
There's the other way. It's combinatorics, like you learned in Dida, where you can either look at it like this, like they looked at it, that we're dividing up balls into baskets, or it's the stars and the
bars and stars.
bars and stars. It's like the bars and stars. It's out, baby.
Okay.
Okay.
Get
We
it.
have all our people, right? This is our list of names,
Mhm.
and we can put it divisor
Mhm.
in any one of these spots. And we have k divisors, so we're basically choosing k different spots out of these to put divisors.
K
We're
minus
choosing
1,
k.
because we can only put K minus 1 divisors.
Yes, sorry, k minus
K-
1, exactly. K minus 1
K
divisors
minus 1,
in these spots. But note that we can't put a divisor at the end or the beginning. So there's n minus
okay, A
1.
minus
There's
1.
n minus 1 different spots. Also, you can't order doesn't matter.
No, that's I don't think that's
Order
the
doesn't matter. Order doesn't matter, and also you can't repeat yourself. This is
Okay,
the same.
yeah, so it's
Okay.
just this,
It's
yeah,
just this.
this,
Exactly.
okay.
It's the same way of computing this.
okay.
It's just two different ways of
I
thinking about it.
explained the stars and bars how I learned it that and quick, but yeah, it's
Okay, not the point of the recitation today. Okay, so the runtime would be at least this amount of options, right? Because for each option you have to check if it's valid, so on and so forth, which equals to n to the power of k minus 1 amount, which is not good. All right, recursive solution. Now remember, recursive solution, we always want to make it smaller, right? At some sort of axis, we want to make it a little bit smaller. So how can we solve this?
but we have like the current student and the current group, and then either we end the group like add the student and go to the next student, or end the group and go to the next student kind of thing.
Yeah, we can either make the amount of students smaller. We can either always solve it recursively with less students, or we can solve it with less amount of divisors, less amount of
Okay.
classes, right? So it's always important to note which axes you can make it smaller, which parameters can you make smaller. So here we have two of them, right? We have the number of students and the number of classes, and we're going to actually do it on both of them. So let's define f, I, and j, the number of friendships, the largest number of friendships that we can honor in a division of the I for students into j classes. Okay, so we're making both I smaller and also j smaller. So now let's define our function. I j equals something and max of, well, sorry, just max, and now we're going to do the different options that we have. Okay, so what are our different options?
Either, like you said, end the group or not end the group, right?
So you want to do either in group or not, but here it's not an element that we can add or not add. We're not checking one group, right? If we have, let's say, we have this one that we made smaller, right? We have this last student that we're basically, now we're going to take him off, right? Because we want to make it smaller. So the I is going to be smaller by 1, let's say. So it'll be smaller by 1. And then j is also can be smaller by, we have to also make it smaller. Because if we don't make it smaller, it's also not good. So what we're going to do is, I'll explain. We're going to take the maximum of s between 1 and I minus j minus 1. What does this mean? What is s? S is basically anywhere in between 1 and I minus j minus 1. Why? Because we're basically saying, we're going to recursively call I minus s. So s is the amount of students we're going to put in this new class. Okay? So let's say here we talk about only adding 1. Right? Now we're talking about adding a certain amount of students into this new class. So this would be S is the amount of students. Now S could only be between 1, because we have to add at least 1. And I minus j minus 1. Why? Because j minus 1 are the amount of classes we have to divide the rest of the students up to. And in each one of these classes, you need to have at least 1 student. So that's why we can't take more than this.
But J minus 1, J is the number of groups.
J is the number of groups, exactly.
So why do
We're
we
basically-
minus it?
Because we want to make the problem smaller. So how can we make the problem smaller? We're basically going to take a certain amount of students, S, and we're going to put it into the jth class. And we're putting them all into one class, into the jth class. This is all going to be the jth class. And then the recursive problem is going to solve it for all of these. For all these, it's going to solve it recursively. Okay? And we have to take the largest S, like not the largest one, the S that gives us the maximum of this.
So
Okay.
S is the number of students I took for the JF for the web group.
For the J group,
For
exactly.
the J.
This is the J group. S is the amount of students we took. And the rest of them, we're basically calling it recursively, given I minus S students, because we had I students, right? And now we took S and put them into J.
Yeah.
So given now less students, what's the
Less
maximum way of dividing them up into J minus 1?
Yeah.
So we put all the S into one group,
Mhm.
and now we have J minus 1 groups of dividing the rest of the students up.
Mhm.
Okay, so we made the problem small. Okay, is this part understood? Before we get to the actual computation.
So it's have to like select all possible S.
Exactly, we have to check all possible S's.
S.
Because we don't know which one. S is the amount of students we put into this new group,
Oh, okay.
into the Jth class.
So
Okay.
why isn't it just between I and 1? Why is the minus J
Makes I in 1, because if we put I students in the Jth group,
What would be
how are you going to put it? What are you going to put in the rest of the groups? Right? If I put in everything,
Great.
if I put in everything into S,
J minus 1 is the minimum I have. Like if I need to divide for 7 groups, I can put everyone but 6 other students
Exactly.
in the same group, and I just need one for
exactly, you need one for each group. Exactly.
Oh, okay.
Awesome. All right. So now this is great. This is the max, but now we need to compute the amount of friendships, correct? The amount of friendships between each group. Okay. So this is where R comes in. R is going to be the amount of friendships in that group. In that new class that we created in J, it's going to be the amount of the amount of friendships that are still kept in that. R, X, and Y is the number of friendships that are in the group that contains from X until Y.
We need to still define it also, no?
We didn't compute it yet.
Okay.
We're saying, given this, we're able to compute it, right? Given this, we can do this dynamically and great, but we have to somehow compute this. We'll get to that after. Okay, so why is it R I minus S plus 1? Because R I minus S plus 1 is the first person,
Here, yeah.
is I, right, is all of them minus S plus 1.
Yeah.
So it'll be the first one. And then until I. So it's basically saying, how many friendships do we have in that last group? Okay, so say for example, X and Y. Get that, Donnie is X. Zerubbabel, great name, is Y. And that's if we have 4 friendships. So our X and Y would be equal to 4. And I'm going to use that to compute, because we're basically adding, if we already knew the maximal amount for these, then we can just add our XY to the maximal. Okay. Now, like you said, given a very efficient way to calculate RXY in O of 1, the runtime of calculating Fij is O of n. Why is it O of n? Because we don't know the size of S. We have to try it for S equals 1, for S equals 2, for S equals 3, right? Because we have to try for the max of S. So we have O of n different calls. Each one will take O of whatever this takes. If it's O of 1,
Just for one group, the Fi and J, right? How do we define it? That is, it's our final function?
This is our final function.
Okay.
Because if we give it f of I, which is n the amount of students, and j is equal k the amount of groups, it'll output the maximal amount. Okay? So j is between 1 and k, I is between 1 and n. Therefore, in dynamic programming, we can solve it in, like Artem said, O of n squared times k time. Because our table, now let's do this again, because I don't want to just wave my hands in the air and say, do it dynamically, let's solve this table.
Where did the K come from?
K is
the amount of groups you have to divide it up into, the amount of classes, right? So our table will be what dimension? What dimension is our table going to be?
n squared.
Not n squared, n by
K.
K.
k, exactly.
Okay.
the amount of groups, right? So J is the between 1 and K, and I is between 1 and N. Okay? And now what's our base case?
We
It's our base case. Depending on S equals 1? Yeah, if I equals like 1, if I minus J equals 1, then we only have one thing, right?
Yeah.
So if I minus J equals 1, so I minus J, so it'll be another diagonal, but I don't think it's the middle diagonal because that would be 0. Instead of the middle diagonal, now it's the
After one.
one below it.
One below it or one above it? Below it?
Below it. Because we want I to be greater than J by 1,
Ah, okay, yeah.
right? So not this one, because when I equals J, I equals J. Oh, actually, when I equals J, that's our base case. It's the middle one. Because if I and J are equal, it would be between 1 and 1, and S would only be equal 1. And therefore, we just do
Just do 1% at each group.
exactly.
So
Exactly. So it would be 0, right?
just 0 amount of friendship in each group.
Exactly. Because each one will only have 1 in each group. It would be 0. And then what is each cell based off of?
Max of
Of S between 1 and I minus J minus 1. So I minus J, so here I minus J is let's say it's fill in this cell. So I minus J is equal to 1. Minus 1, now it's 2. So S is now in between 1 and 2. So you have to check the biggest between adding 1, the last person into this group, and adding the second last person into this group. So how's that going to look? We have, let's say, I people, but we can only take the first 2, right? So we need to check the amount of adding
both of them to the same
both of them
group.
to the same group, or just one to the group, right? So if we add both of them to the same group, because right here it's just J equals 1.
Let's go to like I equals 2. So
Hmm?
can we go to I equal 2 right now?
Yeah, I think when I equals 1, you wait. When I equals 1, or stop. I think when I equals 1, you only have one student, right? We only have one student. So maybe let me try this again. When I equals 1 or 0, we only have one student, therefore it's all going to be zeros. Right? When J equals 1,
Also.
no, not necessarily. If J equals 0, it's all going to be zeros. So we can really do start from 0 index, right? And then it would be all zeros. We have 0 classes. And then when I equals, let's say this is 0, so 1 will also be all the zeros. And then 2 already, we can already start dividing it up, right?
Mhm.
So 2, if we have 2 people and we have 1 class. So if they have a connection between them, if they have a friendship, then we'll have 1. It really depends on the amount of friendships in that new class that we added, right? And now this we can't do, because if there's 2 people, we can have 2 classes actually, but it's just 0. There'll be 1. Exactly. So the diagonal will all be zeros, because then you only have the diagonal, but it could be the n is bigger than k. So it could be this is a lot bigger, and therefore we have more cells down here that aren't bound by this. So now, when I equals 3, we can either choose to add 2. Oh, sorry. When I equals 3, we have to add all 3 of them to that same group. Therefore, it's 3. So basically, when J equals 1, we can also fill it up. It just is the amount of friendships up until the I. So this we can know. Now when it equals 3, but J equals 2, we can either add 2 people to the group or 1 person to the new group. And then we take the maximum of both groups. So what is it when we add both people, when we add 2 people into our new group? It would be the 2 people minus like plus the friendships of adding one person, the first person to the first group. So it'd be like if the two people are in, the next
We
two.
go to J minus one, I minus S, depending on the S, and then we add to these the R.
So it'd be either
Yeah.
like one plus, like if we add two people plus the amount of friendships in the one of just having one person, or we add just one person and we have those two in the previous one. So it's basically based off of all of those.
Previous ones.
Yes. So the way that we could solve it is just by doing it this way. It's a bit of a tougher one because dependent on S and also the function is I minus S. So you'd have to have the I minus S, which is just from the cells above it. And J minus one is just this one. So it depends on the column before it and all the cells above it. Okay?
So where does the other N come from? Why is it O N S K?
Because each cell we need to check all of the cells, all of the different S's, not the amount of friendships. Friendships we can check in O1, all the different S's. So we can have at most N, right? It could be at most N if we have a lot of them. Okay? All right. So now we understood the dynamic programming part. We need to figure out how we can calculate R in O1 time. And this is where it gets a little bit complicated. But the main solution we understood, right? Questions on the main solution. Thomas?
It was in square scale, like Artyom said, yeah. No, I mean, I like, I don't know, like from the table how we're supposed to read the result because you have to account for the most friends, not the.
Exactly. So you have to account for the most friends. So basically, this cell, well, number one, I don't think it could exist because we can't put, oh yeah, it could exist. Basically, the maximum cell is basically we have N people and K groups. So the result will be right here.
Yeah, but wait, how did you define friend? Like the most friends is like the group with the most friends or the most overall friends?
The most amount of friendships that are kept with our division. Because once we divide, if let's say you and Artem are friends and I put you in different classes, your friendship is not respected. It's not saved.
Yeah, I know.
So then, so the amount of friendships that are saved.
Yeah, but with two people it's easy. When you have three, like let's say you have four friends and you have two groups, you can either have a max of three or have 2 and 2, right?
Exactly. So you have those two options, either adding like 2 people into the group, or adding 3 people into the group, or adding 1 person into the group.
So
you check those 3 options based on cells that you already computed.
I don't think I get it, but
okay. Okay. So I'll continue for now, because we still have a little bit more to do. But yeah, if you want to come to me afterwards and we can go over the dynamic programming solution again. Okay, so now how do we compute R? The naive solution is for every X and Y. We'll just check the amount of friendships that are between X and Y, the number of A and B's that are in our matrix, right? We have a matrix that's given to us that says whether each pair is a friend or not. So let's assume that the original input, the matrix of friendships is a matrix that is an upper triangular matrix, such that for every I smaller or equal to J, if I is a friend of J's, it's equal to 1 and 0 otherwise. Okay, so we have a matrix that only the upper half is what we have, and it's for every I and J. If I is a friend of J, that cell equals 1. Okay, so let's say this for this example. Are 2 and 3 friends?
Yes.
Yeah, 2 and 3 are friends because you just look up 2 and 3. And there's a 1 there, so they're friends. And what about 1 and 4? They're not friends.
But why can't I have 2 and 1?
What do you mean 2 and 1? Like here, 2 and 1?
Wait, why is it?
Why is it empty? Okay.
Why is it
Because
zero?
technically, that's the second, actually, I don't know if we're gonna get to it, but the second presentation is about this exactly. That if you want to represent friendships, like whether two people are friends, really it's symmetric. It's symmetric on the diagonal. So really, it should be just a split.
Oh, right, because technically.
If one's a friend of two, and two is a friend of one. Exactly, it would just be symmetric.
Okay.
But they said that because it's symmetric, let's just we'll assume it's only the upper
Okay.
half, because we don't need the lower half because it's symmetric. So we're only gonna pay attention to the upper half. So now how are we gonna calculate R? So an equivalent way, but a little bit weird, to describe A is to say that A, I, and J is the amount of friendships between I and the student J. Right? Because if they're not friends, there's 0 friendships between them. And if they are friends, then there's 1 friendship between them. And we're going to use that to then eventually make it something similar, but there'll be like 2 or 3. We're going to define a new
But you're gonna
matrix. Exactly. We're going to sum them, like kind of like prefix. We're going to define another equivalent, but another matrix, which is basically the same idea, but such that B, I, and J is the number of friends that J has from the group of I until J. Okay, so it's the number Bij is the number, as you can see here, 1 and 5 is the amount of friends that 5 has between the people 1 and 5. Okay, so you basically can calculate each one. Let's say we're calculating the number of friends that 6 has from 3 until 6. You just calculate it by 1 column up from here, because right, this is the friends of 6, right? And we can only take the valid ones from 3 to 6. So from 3 to 6, we'll just sum all of these, therefore it'll be equal to 2. Okay? All right, so remember the definition of B. It's actually kind of important, so I'll write it down. B, I, J, num of friends, num of friends of J in the group from I to J. Okay? Now, how are we going to calculate smartly? By definition, it's just the sum of the amount of friends from I until J that person is friends with J. Right? That's just how we calculated it before. So now let's do this other bit. Let's do this smartly. Let's just take out Aij out of the sigma. And then it's from T of I plus 1 until J. We just took the first element out of the sigma. All right. Now this is something that we know how to compute. This is basically Bi plus 1 and J. Right? By definition, Bij is equal to from I to J, that sum. So from I plus 1 until J is basically Bi plus 1J. Okay, but now we have just Ai comma J, which that one we can look up in O of 1, add it to the previous cell, and then we can calculate each cell in O of 1. Okay?
But we can still take, it's still O of n squared.
Exactly. It would still take O of n squared. Each cell is O of 1. Okay?
How about all the work we did
What?
before? All the work we did before this, like the computing the prefix.
Like what prefix?
No, before this.
Like B?
Yeah, we said
This?
we're gonna talk this one. Yeah.
Yeah, but how? Now we're talking about how do we create this?
Yes. Okay. So
How do we
this one
create this?
and
Exactly, cos
Okay.
n squared. So we're gonna compute it smartly that each Bij is just based off of the one below it, plus the
the current.
something in the matrix, the A matrix. Right? So if we calculate it smartly, rightly, doing it as a homework assignment, the time to compute every cell is O of 1, and therefore the whole matrix B can be computed in O of n squared. We kind of described how it can be done, right? It's just column by column. It's not even just column by column. You do it from the top down. Okay. Now, how are we going to calculate R? Now we have B. Great. How does that help us with R? So we had our matrix A. Now we have our matrix B, right? A is just the friendships, whether or not there is a friendship. B is the number of friends that J has in the group between I and J. And now how do we calculate R? Which R is
Are we
the
supposed to B?
no. B is just the number of friends J has with I until J.
Okay.
R is the number of friends that are within the whole group.
Oh, okay.
It could be I and I plus 1. In B, it could only be J with I.
So sorry, are we on the same problem we were before?
Uh-huh.
Yes.
Okay.
But this is like a side. We like opened up parentheses. We're basically just doing a side problem, which is this is our main solution, but we need to compute the R, right? If we go back to our main one, our recursive formula is based off of R. So we said, assuming that we can calculate R in O of 1, and we can do all this in O of n squared times k. And now we're showing how we can calculate R in O of 1.
Okay.
Okay?
Get some BIF for F from I to J, and then divide it by 2.
Wait, what do you say?
Calculate R.
Okay.
Some BIF for F from I to J.
Exactly. We're going to do the same thing.
And
The same thing we did here with B. We do the same thing with R. Okay? You'll see it in a second. So remember, Rij is the sum of the number of friendships between every one of the group to all the previous ones. Okay? So before we have Bij, which is the number of friends of J in the group I till J. But really, if you want to calculate Rij, you have to sum up all of the, oh gosh.
It's okay.
I just hope the camera gets it. You have to sum up all of the different J's within the group, because this is the amount of friendships J has with the rest of the group. Do we want to sum it for also J minus 1? All the friendships that J minus 1 has with all those before it, and J minus 2 with all the ones before it. So basically, it's a sum of all the different ones before it. So if this is our matrix R, this is our matrix B. So this, the same thing that we had before, right? Well, now it's not 3, 6, and now it's 2 and 6. So here we want to sum up all the friends that 6 has within 2 and 6. And then also all the friends of 5 between 2 and 5. All the friends of 4 between 2 and 4. All the friends of 3 between 2 and 3. And all friends of 2 between 2 and 2, which is 0. Right? So you're going to sum it up. And if you look at this table, then that just equals, now it's the row that we're summing up, not the column. But it's just because we want to take also from 2 to 6, all the friends that 6 has with this group, all the friends that 5 has with this group, all the friends that 4 has between 2 and 4, all the friends that 3 has between 2 and 3, and so on and so forth. We just sum all of these.
It's still n squared.
It's still n squared, but we're going to do it smartly for it to be n squared, because technically each one of these, you have to sum, for each cell, you have to go through at most O of n. So it's O of n to the third power.
Oh.
Okay, I have
But-
a and just have fun.
So we're going to basically, and also you can just note that if you want to do the calculation, right, each one of these is a whole row in our original matrix, right? That's how we calculated this one, is we summed up all these. So this one is just a sum of all these, this one's sum of all these, and so on and so forth. Okay? So now, how are we going to calculate this smartly? Instead of O of n to the third power, we're going to do it O of n to the second power. So by definition, it's just R of Ij is the sum of all the t's from I to j. It's the same exact trick, right? I and t, but instead of before it was t and j, now it's I and t. But we're gonna do the same exact thing. We're gonna take out the first element, and then this is basically equal to R of I and j minus 1. So we know, if we know this, we can just add this and O of 1 because we already computed this, and get our whole matrix, because we're going to just solve it now row by row. From right to left, we're going to solve it row by row, and we're going to fill up our whole table. So therefore, now to sum up
All of x is O1.
our what?
The pre-work of O n squared, and our whole algorithm was O of n squared k.
Yeah.
Everything's O of n squared.
Exactly.
Okay.
Exactly. That we did a whole lot of computations to calculate, to make a data structure that can hold R of every x and y, that we can do a query in O of 1. But in order to do that, it took us O of n squared to build B, and then O of n squared to build the matrix R. But lookup is still O of 1, which is what we wanted. So we show that the time to compute R is O of n squared, because to compute B is O of n squared, R is O of n squared, and therefore we improved the runtime, the pre-processing time from O of n, the fourth power squared to O n squared times k.
Before you said when we like do rework, you called it pre-computation. What did you call it?
Every computation.
Computation?
Yeah.
Nice.
We're gonna have to wait a little bit.
What do you mean?
What do you mean?
What's more?
We're gonna be down after the next question. No, there's no more questions. This was the last question. We're just gonna finish it. And then there was the other, this is why I didn't start with the other presentation, because I wanted to finish this. And then I'll have to do it maybe next time.
That's the other presentation.
The other presentation is it's on how to save graphs in computers, right?
What?
How we can store graphs in computers. We saw here that there was like a friendship, right? It was given us as a adjacency matrix.
Yeah.
Exactly. Those are the two ways, but we just go over that pretty quickly. You
It's
looked
not
at
in the
it.
syllabus. What?
It's because we need it here, and also they want to do in greedy algorithms. They want to do an algorithm that will use them, so we can't just like jump right into it. So that's why they wanted me to teach it. Does it help if I press the on in the middle of the class? Like, will it prolong it or no?
Maybe. I mean, I think it's usually like 1 hour and a half from the time you press on the first time, but I might be wrong.
Yeah.
I think it was later than 5. Right, because you were busy.
He opened like 5 minutes early. Or was he done when you got here?
No, it was 5 minutes early. I opened it up. It's always an hour and a half.
Yeah.
Hey, here we go.
Okay. So wake up.
Show it still. Okay.
Oh
You
yes,
don't
no, I'm still
stop
recording.
recording.
I'm still
Oh.
recording. It just shut off. I'll just.
Thanks.
Oh, you're right. I have to make sure. Oh no, the camera's on. Why is it? Oh, because I just turned it on. That's smart.
I don't know. One time it stopped. So
Oh no, Lotem wasn't able to make it in.
I was thinking.
Okay, so our pre-computation time of our R matrix is O of n squared, and therefore the pre-computation is O of n squared times k instead of O to the fourth power times k, because in order to calculate R, the naive way is takes us O of n squared for each one. So now it'll actually take us O of n squared k
Adriel, you lost the camera.
again. It's okay, we're just finishing anyways. Okay. So instead of O of n, why is it so complicated? Still one that's flat. And O n to the fourth power times k, because the naive way of computing our each r x y would take O of n squared. Now it only takes O of 1 for each query. So now we improved it to O of n squared times k using pre-computation. Now to sum up this recitation, it was an advanced dynamic programming. We had 4 different techniques. What were they?
Pre-computations.
Pre-computations was one. Yeah.
Solving a different problem.
Solving a different problem. What else did we have?
And multiple functions.
Multiple functions,
Yeah.
exactly like we did in the previous one. And what was the last one? It's not really a technique, but it was just not having a set amount of recursive calls. Like in Fibonacci, you only have 2 recursive calls, and a bunch of the ones we saw here, it's a not known amount of function calls. It depends on the range. So those were our 4 things. Now homeworks, you guys are way ahead of the Israelis. I didn't even start dynamic programming with them. We can start next week with them. So I'll just release the homework early, because why not? There's only gonna be 1 homework on dynamic programming. The other homework, the advanced one that you were supposed to get, is gonna be not for you don't have to give it in. It's not gonna be graded, so I'm gonna upload it with the answers. I highly recommend going over them, even if you don't solve it yourself, just to make sure you understand the answers. I try and solve it obviously first, but yes.
are we doing the 10 best credit homeworks this semester? Or?
So exactly. So I said 9. I'm sorry I didn't get already on the English group too. I always have to remember that anything that I like update down, I have to update you guys too. But because there's only going to be 11 homeworks instead of 12, now you only have to give 9 of 11. Okay. All right.
So
See you guys next week. I'm just going to stop the recording.
Sure.
For you to ask any
And I
questions.
was gonna do the graph next week.